Here I'm going to be answering a past paper question proving de Moivre's theorem by induction. It came up in 2018. As with all induction questions, the first thing we do is test the first case. In this case it's n equal to 1, but that is the cos theta plus I sine theta all to the power of 1 is equal to cos 1 theta plus I sine 1 theta. And that is true. Next thing we do is make the assumption that it's true for n equal to k. So, assuming it's true for n equal to k would mean that cos theta plus I sine theta to the power of k is equal to cos k times theta plus I sine k times theta. We're going to use that assumption to prove it's true for n equal to k plus 1. So that test that we have to do now is to show that cos of theta plus I sine of theta to the power of k plus 1 is equal to cos of theta, k plus 1 theta plus I sine k plus 1 theta. So here we have a left hand side and the right hand side. What I'm going to show that if I expand out the left hand side, it's going to be equal to the right hand side based on a previous assumption. So de Moivre's theorem ends up being a little bit more complicated than the other induction proofs based on the fact that we have to use some trigonometry, we have to use some of the compound angle formula in the tables, but we'll get to that in a minute. The first thing I need to do is expand out the left hand side of my equation up there. So cos theta plus I sine theta to the power of k plus 1 is just equal to, we're just dealing with the left hand side now, cos theta plus I sine theta to the power of k times cos theta plus I sine theta to the power of 1. So what I'm going to do is I'm going to use the assumption that I made at the start that cos theta plus I sine theta to the power of k is equal to cos k times theta plus I sine k times theta. And I'm going to use that down below to expand that. So that's equal to cos k times theta plus I sine k theta all times cos of theta plus I sine theta. Now what I'm going to do is expand out the brackets. It will look a little bit messy, but I will tidy up fairly quickly. That's just equal to cos k theta times cos theta plus cos k theta times I sine theta. So I'm just going to put the I in front of that. Plus I sine theta. Sorry, that's I sine k theta times cos theta plus I squared sine k theta times sine theta. What I'm going to do now is I'm going to keep my terms involving I together and my terms which don't involve I, because I squared is just equal to minus 1 from complex numbers, and I'm going to bring them together here. We're just left with cos k theta cos theta minus sine k theta sine theta plus I outside of cos k theta times sine theta plus sine k theta times cos of theta. Okay, that's a bit complicated, but hopefully what we'll see is after using the tables we're going to be able to narrow this down. What I want you to think, just for simplicity's sake, that's angle A, that's B, that's angle A, that's B, that's angle A, that's B, that's angle A, That's b. Now, let's have a look at the compound angle formula in the tables. If you have cos A times cos B minus sin A times sin B, that is a formula we have. So that is just equal to cos of A plus B. So this first part just tidies up to cos k theta plus theta using the tables, given that we have cos of an angle times cos of an angle minus sine of an angle times sine of an angle. Then if I look at the second part, I've got cos of an angle times sine of an angle plus sine of an angle times cos of an angle. Well, that just gives me this sine times cos plus cos times sine. That just gives me sine of A plus B. So this left hand side just tidies up to I sine k theta plus theta. That's just equal to cos, if I just factor those out, theta k plus 1 theta plus I sine k plus 1 theta, which is what I'm asked to find here. So my left hand side does equal the right hand side, and so therefore by induction I've proved de Moivre's theorem. So that means it's true for n equal to k plus 1 if true for n equal to k. It is true for n equals to 1, and therefore it's true for all positive integers.